do basic quantum computing, just so you can see what quantum computing works on. And for this, for some reason, I had great difficulty getting the library we need to simulate quantum computers to install anywhere. The only place I found was this environment, Python Anywhere, which is like Google Colab, but for some reason, the library here works. So you can use it, you can make a beginner account for free, and you'll end up with a bash console like I have here. Looks like maybe I'm going to need to refresh. There we are, and log in again, okay. And there, I have a bash account console I can use to do encryption, just like we have done in Google Colab. Here you get bash instead of a Python environment, you get a bash shell. All right, so let me try to make these both fit on the screen more or less. Okay, so once you're in, you get to a bash console, and now you can install Project Q. So this will install pip, and this will install the Project Q library. All right, and hopefully that error doesn't matter. We're going to see. Yep, looks like it worked. Error parsing dependencies. Expected right parentheses after version specifier. It's upset, but we might be all right. Hopefully I can ignore the errors. Or maybe I'm not going to work. Let's see what happens. I think I have this file already in here, nanoq1. I do. So here's how you do it. You import measure. That's going to measure something, so it moves from an uncertain state to a certain state. Here's the main engine. And so we're going to have a default qubit in state 0. And all I'm going to do is 10 times, I'm going to create a qubit and measure it and print the result. All right, so let's see if this will run. I might have trouble because of those error messages. Let's find out. I get out of here with Control X and then Python Q1 .py, and it runs. Okay, so those error messages don't matter. So what I did is I measured a qubit in state 0 10 times, and it's always 0 because it's right at the top of the Bloch sphere. It's not in an uncertain state anyway. So that's what you expect. This is a normal bit, a normal that we'd have. What we're going to do is flip it with the X gate, and that will rotate it by 90 degrees. 180 degrees. 180 degrees will move it down from state 0 to the state 1. So that's Q2. Let's look at that. Nano Q2. All right, so I have qubit in state 0. That's what's created here. And now I'm going to put it in state 1. So I'm going to make 10 qubits, and each I'm going to run it through an X gate, and this is how you do it. Be sure to import the X function from Project Q ops, and then you do X pipe qubit. That will do it the way measured pipe qubit worked up here. So this will rotate it through the X gate and then measure it. So these 10 should all be 0, and these 10 should all be 1. So if I run that one, that's what I get. The first one is all 0, the second one is all 1. So this is normal digital computing with zeros and ones. That's what we got so far. We haven't done any of the quantum stuff yet, so we want to do that next. That's the superposition state. So let's look at that. That is Q3. Okay, and so what you do, this is the certain state, and now you run it through an H gate. And an H gate, instead of X gate changes a 0 to a 1, an H gate changes a certain 0 into a superposition state that has a 50% chance of being 0 and a 50% chance of being 1. So the second list of numbers here should be half zeros and half ones. So if I run that one, that's what happens. The first one is all 0. The next one is some ones and some zeros, which is what you should see in an uncertain state. All right, so now we can do entanglement, and that's Q4. So Q4 is here. All right, so now what we do, we make 2 qubits, and we rotate one with H so it becomes uncertain, and then we have C0, which is entanglement. So this entangles qubit 1 and qubit 2, so they're always synchronized. When measured, they will always have the same value. So the original qubit I created was in, qubit 2 was in a certain state of 0, but now it's entangled with an uncertain qubit, so they should both be uncertain, but always the same. So if I run that one, then I get 2 qubits, and now they're uncertain. They both flip randomly from 0 to 1, but they're always the same. If one is 1, the other is 1. That's what entanglement does. One qubit must follow the other. All right. And now you can make circuit diagrams. Let me see if this is going to work. This is Q5. Now the funny thing about this is to make the circuit diagrams, you have to make a PDF file, and for some reason you have to first make some other kind of file, a LaTeX file, which you have to convert to a PDF file. So it's kind of silly, but that's how it works. So if you run this thing, you have to put the output somewhere. So I'm going to run Python Q5, and I'm going to put it in, say, demo5.txt. So it's going to run it and create a LaTeX file. So now I have to click Files to get that file. And there are files somewhere in this, yeah, here we are, Files. And somewhere down here is that file, demo5.txt. There it is, from today's date. Okay, I can download it here. So I download it, demo5.txt, in my downloads folder. And now, converting it, I had a lot of trouble. And again, the only thing I could find that worked was to use an online converter. So here we go. I choose my input file to be demo5.txt. I choose my output format to be PDF, and then convert. And it's processing, and it's done, so I can download the PDF to demo5.pdf. All right, and I can launch it. And now I see my glorious, so there is a diagram of my circuit, a Hadamard gate and entanglement on the 2 qubits. That's what it is. This is the way you draw circuit diagrams for quantum computing. And since everything is working, I should be able to do the next one, which is Q6, I think. Let's give it a shot. I go back to the code. Let's see how to get there. Wallet, Brave, history, extensions. That's not the right thing. It's here. Here we go. Consoles. There's my console. I think this is the one I'm using. Okay. I think I have a Q6. Maybe I called it something else. Circuit with 3 qubits. Q5A, perhaps? Demo A, well, I'll just make a new one. So nano, I'm going to call this one Q6.pi. I'm going to put in this code. Well, this code is what creates a diagram, circuit with 3 qubits. Okay. This is going to have 3 qubits connected by H entanglement and another H. So there's the code. All right. Control X, Y, enter, and Python. All right, Python Q6, output Q6 dot text, I think. All right. And now I want to download the text, so I go here to Files. I find q6.txt and download it. Then I upload it in this this thing. How do I convert another? Yes, convert. I'll just go back. There, okay. Then choose file, q6.txt, there we go. Convert to PDF, convert, there we go. So it's converting and it's done. I can download it, there we are. q6.pdf, and there it is. So again, this is what it is. I have 3 qubits. This one goes through Hadamard and is entangled, and that one goes through Hadamard and is not entangled. And so that's what the diagram looks like. And if I want to see what the output looks like, then I use this script, which just creates the same circuit and just shows me the measurement. See the qubit values, and it looks, so let me do this. And it's going to do it 10 times and show me the output. So that's going to be here. Okay, I need to go back to my bash. Which is going to be consoles, and the first console, okay. And now I'm going to nano q6a.py and put in that code and save it, and then run it. All right, and there we are. These are the 3 qubits, and the entanglement means the first one and the third one are always the same, and they vary randomly, and the one in the middle varies randomly in an uncorrelated fashion. That's what that circuit does. So that's the game, and so there are some challenges here. We have to create some circuits that match these diagrams, and gives you a chance to play with quantum computing to understand basically how it works. Remember, what you're doing here is like very simple computing, like with individual transistors. And the real quantum circuits that will do something like crack encryption have many of these gates in a complicated pattern to do the necessary transformation of the data. So that's it for that one. We stop this.